Hello matrix. Alright, let's start today's lesson by looking at the work energy theorem. So in the previous lesson we looked at how you're going to determine to work out work or energy. Alright, so let's recap. We said that we can work out or determine work by the formula W, and it is for a certain force. Let's say the work done by an F applied force equals the force times the product of the delta x cos theta. Alright, so that is our basic formula for a certain force or the work done by a certain force. Now let's look at a scenario where there is more than one force operating on a certain object, and we have to determine what is the net work done on that object. Now let me use an example again. So let's say we have a slope and we have the angle of the slope as, let's say, 30 degrees, or okay, and then we have an object that's going to start moving out of rest. So, but let's say there is, and I'm always going to do this so that I don't forget it, there is friction. So the moment that object starts to slide down in that direction, let's say it's going to move from there to the bottom, and let's say that's going to be a delta x of 6 meters. Alright, now the moment I ask you for the net work done, it's just like net force. What is important? What do you have to do first? Draw a force diagram. Alright, so how's my force diagram going to look? My free body force diagram. It's going to be my the normal force, my weight of gravitational force, either Fg or W, small w, and it's going to be my friction working in the opposite direction of my displacement. So there's my free body diagram. Now if they would ask me at the moment, and it might change guys, this is 2025 when I recorded this video, and it might change again. I hope it does, but at the moment you're not allowed, when you draw for the matric end paper a free body diagram, you're not allowed to draw in the for weight its components, which doesn't make sense for me because we're going to work with the components. Okay, so what I'm going to do is I am for myself going to say, listen, there is a component of my gravitational force parallel to the surface, to the slope, and there is at a 90-degree angle or perpendicular to the slope is my W or my weight perpendicular. So I'm immediately going to draw in my two components of weight. So those are all of the forces acting on that object. Now, if I want to work out what would be the net work done, I can either first go, if I have all those forces, I can say, what is the net force? I can do that, but it's not always possible. So now we're going to look at what does the work energy theorem states. Now the work energy theorem states the following, and I'm going to just read it to you quickly, that the work done on an object by a net force is equal to the change of the object's kinetic energy. So what does it mean? It means that the work done by my net force, so there we go, equals my net force times delta x cos theta, that we know already, but that would then equal the change in the object's kinetic energy. And we know already that the change of kinetic energy, the moment I see that triangle there, it means always final minus initial. So it's going to be my EK final minus my kinetic energy initial. And that would then be the work done by the net force. So it's going to be work done by F net. Now the moment I have that, it means I have to now, let's leave that part first out, because you're going to see it's going to become quite hectic. You almost have to turn your, your book landscape wise to get everything in. So let's start by looking only at this. That means that I will have to work out what will be the work done by the normal force plus the work done by my gravitational force parallel to the slope, plus my work done by my weight perpendicular to the slope, plus my work done by my friction. And now, as you can see, there's 1, 2, 3, 4 different forces acting on my object, right? So if you want to use just your weight, your gravitational force here, instead of the two components, you can do that. Just remember, then you've got to work then with this angle, of course, of 60 degrees. So you're going to then say cos 60 degrees. Okay, but let's not confuse you now. Let's stick first. So I'm going to now work with the two components of my gravitational force, parallel and perpendicular. Now, what do we know about a force acting at a 90-degree angle to the displacement? We know that that is going to be, in any case, zero joules. But let's first write it in. So that will be then, okay, that will be my normal force times my displacement cos 90 degrees plus parallel there. So I've got to work out what is my weight. My weight is my mass times gravitational acceleration, mg, and it's going to be parallel sliding down. I always say it slides down to hell because it's sin. So I'm going to use sin 30 degrees. But remember, that is now only my weight parallel. Now I still have to say times delta x to get to the work done times cos theta. So in this regards, my cos theta is going to be, because that component of weight and my displacement operates in the same direction, so it's going to be cos 0 degree plus, okay, the weight perpendicular. What is the work done by the weight perpendicular to the surface? All right, and that's going to be my mg cos theta, which is my weight perpendicular, times delta x times cos 90 degrees, because it operates 90 degrees to the angle, plus so that is that one, that one, that one, and now I'm going to get to the friction force. So and now I'm going to say, okay, so it's my friction as my force times delta x, my displacement down the slope, cos, and what is the direction between the displacement and my friction? 180 degrees. All right, I know that's going to equal the change in kinetic energy. All right, but immediately the moment where I have 2 cos 90 degrees, that will then become 0 plus, so I've only got that one, so that's my weight, sin 30 degrees times my displacement cos, and now because it's both in the same direction, cos 0 degrees, which would give me 1, so that will then be my mg sin 30 degrees, which is only my force, right, okay, times delta x cos, and it's going to be 0 degrees, plus, now that one again becomes 0 work done by the gravitational force perpendicular to the slope, plus, and because I've got 180 degrees there, it's going to become a minus f delta x, cos 180 degrees gives me that minus, equals, and now on that side I'm going to have my kinetic energy, or the change in kinetic energy. So as you can see, guys, just really be very systematic. So for every force, you're going to say, okay, what is that force? The work done by that force, plus work done by that force, plus work done by that force. And that brings you then to your net work done by the net force. And that will equal then the change in kinetic energy. So in this case, for instance, I will now have to write all that, and on that side I will have to still continue. Now, where am I going to use this? Now, a typical, all right, let's go back. We're going to do one just now as a sample. Okay, so the typical way you're going to use this formula, which is the net work done equals the change in kinetic energy of an object. The typical question would be, they're going to say to you, okay, it is sliding down, it starts from rest, it's sliding down, determine the final velocity. Now immediately I know, okay, so I've got all my forces, I do have the friction force, I do have that angle, so I can work out, I do have the mass of the object there, so I can work out that force, that force, that force. I have all the forces, I have the displacement. Where is the unknown going to be? The unknown is going to be where? On this side. Because here I'm going to have half mv final square minus half of the mass v initial square. But of course, when it starts from rest, it's going to be initial 0, and I have to determine the final velocity here. So there is the one that I'm going to determine. Alright, so I know it looks like a lot, but let's start systematically with a typical question. So the question looks like this. It's question 5 from a old matric paper. Okay, the question looks like this. Okay, they say they've got a buoy up here. It's going to go down a slope of 20 degrees. Then they've got a P there and Q there, 2 points. Okay, and they say it's got an angle of, yeah, we've got that already, 20 degrees. A constant frictional force of 50 Newton. So F, frictional force, equals 50 Newton, and it's going to work against upwards the slope. Why? Because he is moving down with his skateboard. As it moves from P to Q, consider the buoy and the skateboard as a single unit with a mass of 60 kilograms. So that is the buoy with its skateboard, and it equals 60 kilograms. I'm not sure if you can see that, but I'm going to have, in any case, the question here on the side. Alright, so what else do they give me? They do give me that P and Q is 25 meters apart. So immediately I realize, great, I've got delta x. I've got my friction. I've got my displacement. I have my angle. Alright, now let's wait for the question. Now it says, draw a labeled free body diagram showing all the forces acting on the buoy while moving down the ramp from P to Q. So let's have our free body diagram, and we know it's going to be, if this is my slope and that is my buoy, then I've got 90 degrees to the slope, my normal force. My weight or gravitational force will always be straight down to the center of Earth. So that is Fg, or weight, small w. And the third force is going to be the friction force, which operates parallel to the slope, but in the opposite direction of going down. And guys, I always can tell you, you can always check the marks. if there is on this one that I see that it's got 3 marks. Now that 3 marks is a giveaway for me to make sure I've got 3 forces here. So do I have 3 forces? Yeah, 1, 2, 3 forces, 3 marks. Okay, continue. The skateboarder passes point P at a speed or velocity V initial and passes point Q at a speed of 15. So we've got our V final as 15, and they did not give me the initial speed when it passes point P over there. Then I say the skate, I got 15 meters where as it passes Q. Ignore rational effects due to the wheels of the skateboard. State the work energy theorem in words. Now guys, the moment they ask for a definition, alright, and it is like it, you have to write the definition as it stands on your examination guidelines. But the moment they ask you for a certain definition, you know what, that's actually a clue. It's a clue for you to know which formula do you have to work with in this problem. So it's a giveaway. Alright, so let's say, so the moment they ask me, use the work energy theorem in words. Now they say in the next question for 5 marks, use energy principles. So you see, we can't use any of our movement formulas. We have to use only our energy principles. And because they've asked me for my work energy theorem, I'm going to work with that one. So, where do we start? We say, alright, what is the forces working on it? My work energy theorem states that my work done by my net force equals the change in kinetic energy. So my energy is going to change from a velocity initial to a final velocity of 15. So I'm going to start with having my work done by each of my different forces. But I personally like to work rather with my 2 components of weight. So here I'm going to work with my weight parallel, and here I'm going to work with my weight at a 90-degree angle. Alright, so now I'm going to break this up. So I have to write, okay, so it's the work done. So W net is the work done by, let's start with the friction force. So it's a work done by the friction force plus work done by the normal force plus work done by my weight perpendicular plus the work done by my weight parallel equals the change half of my mass times V square final minus half mass V initial square. Now I'm going to have to break this up, but I'm already going to, in the place of my work done by my normal and my work done by my perpendicular, those 2 I'm going to just substitute as 0 joules. So what I'm going to be left with is, alright, so that's going to be F delta X cos theta. Now that theta we know is going to be 180 degrees because the movement or the displacement is in that direction, friction is in the opposite direction, so the angle between my force and my displacement is 180 degrees. So that's going to be here, so I can already put it in as 180 degrees. Plus work done by my normal, 0 joules. Plus work done by my perpendicular weight, 0 joules. Plus, okay, so now I first got to work out what is the force parallel. And that is mg sine 20 degrees, and that's only my force, times what is my displacement, delta x, cos, and now because that force and my displacement is in the same direction, it's going to be 0 degrees, equals, and now I'm going to have half of my mass, and I'm going to have V final square times V initial square in brackets there. So I'm still only by my formula. And now I'm going to start to substitute. So let's start with our substitution. We've got the friction force as 50 newtons time, what was the distance, this displacement, 25. Cos 180 degrees gives it a minus. Plus, the mass we've got as 60 times 9,8 for my weight, sine 20 degrees. Okay, so that is only my force times 25 meters, and cos 0 degrees is 1, equals half the mass, which is 30 kilograms, and my V final square is 15 square, times the initial square, which is my unknown. Alright, so let's start to work that one out. So here we've got a 50 times 25, that gives me minus 1250 joules, plus, if I look at this one, 60 times 9,8 for the weight, times sine 20 degrees. Okay, and that is still times 25 times 1, that gives me 5027,696. I'm just going to leave it as 3 decimals there, equals, and there we've got the 15 square times 30 gives me 6750 minus 30 the initial square. Alright, and let's determine this quickly so I can bring that over. That becomes then a minus. So I've got to have that plus 1250 equals minus 5027,69. Where am I? 696 equals this. So I've got a minus 30 the initial square equals a minus 2972,30 on that side. So my V initial square is going to be that divided by 30, and my minuses is going to cancel out. So I've got 99,768. So my V initial was 9,95 meters per second. Alright, so as you can see, guys, I know it looks crazy. Just stay on it and just say every time force times displacement, cos. What is the cos? The angle between the two. But I always try to have my cos as either 0 degrees or 180 degrees. So I always try to have my forces in the same lineup, so either working together or opposite. Of course, you could have worked with a weight, and then you would have not had, then you only would have had one FG or weight, and then the angle between them would have been 20 degrees, so that would have been 70 degrees, if that makes sense. But you'll see that when you start to work through old test and exam papers, that that on the memo there's different options. So as long as you have a way of working that works for you, then stick to that. That option will be on the memo. For instance, like I did it now, working with the two components of weight. All right, so there we go. That was a typical question where they've given me the two point P, point Q, and they asked for the initial velocity. Great. I hope it works for you. I hope it works for you. Believe in yourself. You can do this.